Okay, so just let me, yeah. So can you see my screen?
Yes, madam. We
Yes,
can
yes,
go to.
it's clearly seen. No
Oh,
issues.
okay, so then I think we can start. So hello everyone, I am Urbi. I am currently working in the Department of Computer Science and Engineering at IIT Kanpur. So today we are going to talk about design, analysis and implementation of physically unclonable function-based authentication framework for Internet of Things. Okay, so it's kind of a nice intersection between hardware security as well as how we are going to apply hardware security for specifically for Internet of Things devices. Okay, so first of all, before going to specifically to Internet of Things, let us first understand that where do we need security. Okay, most of us know that, but just for a recapitulation, I would say anything which is e or smart, okay, be it automotive, big data, e-health, smart home, e-voting, unmanned air vehicles, smart grid, e-commerce, supply chain or subscription system, whenever there are some uh, money or user or in today's world more essentially where user data is involved, we need security. Okay, so now when we talk about making a secure system or building up a system which is unbreachable, we have to think about two things. Number one is what is my root of trust, and the second thing is what is the adversarial model. Okay, so what is these two things? Root of trust means when we create a crypto system or a secure system, we always have to trust a particular entity. Okay, that can be a third party, that can be your memory, that can be a software, okay, that can be your computer architecture, right? So it depends on what you are building up. Okay, so you have to trust that this particular part cannot be compromised. Given this assumption, you can build up a secure system. If everything is untrustable, then there is no point of security over it, right? And the second thing is, when we are building up a system, uh, how much capability we are giving or we are considering the attacker has. Okay, how much resource it has, how much it can uh, it can have, how much access it can have into our system. Okay, so we will see this kind of thing, that how when we implement security system, how we jeopardize with the adversarial model that actually lead to serious threats. Okay, but before going to that, let us first see some example of root of trust. So suppose somebody is working on operating system. Okay, we know that the operating system has to be very much secure, otherwise somebody will inject a malware and we are doomed. Okay, but when somebody design an operating system, they assume that the architecture of the processor is secure, nobody can tamper the hardware beneath it. Okay, when somebody design the secure boot, I mean the bootloader program, when we power on the system, right? So they assume that while we do secure boot, it is secure because we actually take up a key which cannot be tampered by an adversary from something called trusted platform module. Okay, it's a very small memory that lies in the system. So when a person will be designing a secure boot system, it has to trust that that key is uncompromised. Otherwise, anybody can use that compromised key and change your bootloader program. Okay. Now, somebody who is working on network security. Okay. So suppose somebody is making a firewall. What it has to trust is that the routing rules that it is writing in the router box, nobody can tamper it. Suppose I am not allowing a port to accept any HTTP GET request, but if somebody has access to that routing table and port open make that port open, then then the security will, I mean, the network will be vulnerable. Okay. Now let us go down a little bit into the system. So now we talk about the cryptographer. So whenever, I mean, though as you guys are already aware of security, so but I just want to give a brief about it, that when we talk in WhatsApp, right? So I mean, last 2-3 version before, we used to see that when we initiate a talk with some friend, we used to see that this chat is AES-128 end-to-end secure. Okay, so that means when you have created a chat with one of your friend, then a session key has been generated using using AES algorithm. Okay, now somebody who is working on developing AES, okay, AES is a symmetric key, right? Maybe RSA, ECC, which are the asymmetric cryptography. So they just ensure that the algorithm is mathematically robust. Okay, nobody can break the design mathematically. Okay, but then when we implement this kind of cryptographic algorithm in FPGA, what happens that it is implemented in I will not say only FPGA, it can be ASIC also. So what happens is that it is mapped into some registers, memory, data path, control path, right? And as these hardware components actually take powers to run the coprocessor for this cryptographic algorithm, and as the operations that is happening in this algorithm are key dependent, the power consumption also become key dependent. Okay, so if somebody can tap the power while we are running a cryptographic protocol, it can actually get some information about the keys that are getting used for this particular encryption round. Okay, but when somebody is developing a cryptographic algorithm, he assumes or she assumes that the Verilog or VHDL code that I'm writing on for the FPGA or ASIC would be secure. So it will not have any leakage from the power perspective or EM perspective or fault perspective or even timing perspective. Okay, so these are some side channels. So in hardware security, side channel attack is a very prevalent area in which we work. Okay, now let us go more deep down. IoT devices. Okay, so a lot of people works on machine learning, big data analysis, and making business decision on the small sensors, actuators that are put up into the IoT devices in a power plant or manufacturing plant and all, and collect data from them, right? But they do not see that the source of generating the data, that is the sensor, is somebody modifying it, or while the data is coming from that particular IoT device through some lightweight communication protocol like Zigbee or Bluetooth or whatever, and coming to the server, somebody is manipulating it in between. Okay, so when we design IoT devices, the trust is that the IoT devices will be resilient against side channel, any kind of device fault or manipulation attack. Okay, finally we will go more down. Okay, now we have come to the hardware platform. So if we have a function for which we are designing a hardware, everything ultimately is going to the hardware, right? So what we basically use AND gate, OR gate, XOR gate, flip-flops, memory element to have a digital design of the particular hardware, right? So your processor is nothing but a digital plus analog system, right? So specifically for digital designer, we implement all these logic gates like AND gate, OR gate, XOR gate using standard cell or technology. You may name like CMOS technology. Okay, so now when we are fabricating these chips, people can change at the cell level, and can actually change your AND gate to NOR gate to make it work in a different way. Okay, so you can understand that these kind of attacks at the time of fabrication is very hard to detect, but they are possible. Okay, so when we are making a hardware, we assume that the standard cell or technology will not be tampered by an attacker. So now we will come to the adversarial model. Okay, so suppose I am a manufacturer of IoT devices. Okay, I am assuming that I will send data in plain text to the cloud server. Okay, without any encryption or integrity verification and all, and my data will be safely reach the cloud. Nobody, no attacker can tamper that data. Is it a valid adversarial model? Tell me. Anybody can comment. Do you think the assumption, I mean, what do you think that are we underestimating the attacker or we are overestimating the attacker? Any comment?
Yeah, I have allowed the mic. They can answer.
Hello.
Okay, thank you.
Yes, yes. Yes, please.
Ma'am, basically, cryptography code will be generated for efficient in VHDL or FPGA or ASIC. There are so many of IoT devices. If we using the random number generation, pseudo random number generation or true random number generation, by
Yes,
XOR,
that is also
by
very
XOR,
important.
yeah, please XOR post processor design of 64-bit using a SIFT, CPO and FIFO. Based on basically tree-based interleaving process or 8-bit random number generation proposed algorithm. So then how is the basically semantic of will be generating for encryption and decryption as well as for both end as well as with ciphertext for using the different types of the plain text as well as a ciphertext both for encryption as well as for decryption in random sequence generation for symmetric encryption as well as asymmetric encryption cryptographic process.
No, what is your question? Can you just summarize? Are you giving a comment or are you asking a question?
No, I am asking question that FPGA and ASIC in VHDL used in cryptographic protocol. How is the method to use for that? If I use in example, take as a TRNG device, you 64-bit using generation XOR gate, then how this cryptographic VHDL code will be work? Basically, a working of cryptographic VHDL code in FPGA as well as other or ASIC use.
Yeah, I mean, so you want to say that how we implement a cryptographic algorithm in FPGA? Is that your question?
Yes.
Oh, there are a lot of VHDL Verilog code for AES itself, which are available in GitHub. Okay, so see, the thing is that an AES algorithm, it can be written in C, C++, Python, right? Do you agree? AES algorithm, can you write in C?
Yes. Yes.
Right. So now I will not go to AES. Okay. I will give you a small example of a counter. Okay. So suppose you want to count something. So what will you write in C? That for I equals to 0, I less than n, I plus plus, count equals to count plus 1. Okay. Now, actually, when you will compile and then whenever you will be executing, so what will you get? An assembly language code for that, right? Now that code is what? Assembly language code is just giving some instruction to your processor, right? Ultimately, it does not happen as count equals to count plus 1. What happens that in memory, I mean in our processor, there are some register which will be initialized by 0. Now till that I value starts from 0 to n, the count, the register which is holding the value 0 will be added plus 1 plus 1 plus 1 plus 1. So that the thing is that whatever we are writing in C, we can write in Verilog. We can write an absolute analogous code in Verilog, but the advantage is that Verilog code will directly run into the hardware because the code is written by using just your memory values and the logic, hardware logic. Okay, so you can say that, ma'am, today I have written a Verilog code. Can I Verilog code for AES? Can I run it into my PC? No, you cannot. Okay, but what you can do, you can create a chip, which is nothing but the application specific IC, which is ASIC. Okay, which have this co-processor of the AES algorithm written in Verilog or VHDL, and then later on it can be plugged in with the motherboard of your CPU. Or if you are using FPGA, you can burn the bit file and run the algorithm. You can give input from your, you can connect your FPGA with your PC, and then you can actually send input from the PC to the FPGA and get it back. Okay, is your doubt cleared? So have you run anything ever in FPGA? Have you tried anything?
Yes, yeah. Hello. Yes.
Yes.
Yeah, our proposed TRNG in Xilinx ISE 9.2 using the
Xilinx is a tool, or I would say Xilinx is a FPGA board.
yes,
right?
yes, ma'am.
Yes.
Yeah,
So
Xilinx.
you have a TRNG, right?
Yeah, Spartan, Xilinx Spartan. It is the
Spartan
hardware
chip.
part, Spartan. But
Yes.
I am asking to our proposed TRNG, ma'am, 3-stage ring oscillation and 5-stage ring oscillation, 4-bit shift register, 4-class multiplexer, 2-bit up counter, and serial input, parallel output register. CPU.
Yeah. Whatever, it's a design, whole hardware design. Yes. Now,
Yeah.
what is the hurdle that you are facing?
Yes, sir. For IoT devices application, in terms of side channel fault manipulation attack. After that, generating a schematics, our proposed TRNG. So in VHDL code, then side channel effect is affecting in which parameter affecting? I am asking to that, fam.
I see. So you are trying to say that if you implement your proposed TRNG in an IoT device, what kind of side channel attack can be done on it, right?
Yeah, sure, ma'am.
Yeah. Okay. I now understood your problem. Okay. So now, if you see the TRNG design, so ultimately we get raw 0-1 bits, right? Which we sample in the last D flip flop, right? So D flip flop is nothing but a memory element. If somebody can track that that flip flop's power consumption while it is changing from 0 to 1 or 1 to 0, then it can guess some idea about what TRNG bit it is producing. Okay, so in ASHES, there is a workshop which is related to CCS. CCS is one of the best security conference. So there's a workshop named ASHES, which is actually on hardware and side channel security. This year only, there is a paper on loop path. So loop path actually use this kind of deep flip flop. Okay, part of it is also RO. So there they have actually shown that how this kind of path can be prone to side channel attack. So you can definitely look at this paper and you will get an idea that what kind of analysis you must do to make sure that your TRNG is not leaking any information. Along with that, I will say that just go to Google Scholar and search like TRNG plus power side channel. Okay, you will get a lot of papers. Okay. So now we will go forward. So hardware security, actually, as he was correctly saying, concentrate on the last 3 topic. Okay. So what is the role of hardware security? First, we do the analysis of side channel attack. Like he has said that we check that when we implement a cryptographic protocol in a hardware, or we implement a physically unclonable function in a hardware or TRNG in a hardware, whether it is leaking any power or EM traces that can leak the information which is need to be hidden. Then the another thing is that another thing that we cover is that how we actually implement a hardware for the cryptographic algorithm. Okay, so that is a very tough job. That's why it is very slow in development time, but it is faster in execution time. Okay, because we are at the device level. We are talking about at the device level, so no like compiling and code coming from the memory to cache to the CPU, and these kind of things are not happening. We are dedicatedly creating a coprocessor for a particular cryptographic algorithm. That is why it is much faster. Okay, now hardware fingerprinting of key management, which is the topic for today. We can do even hardware fingerprinting using physically unclonable function. How? We will see that. Next is detection of hardware Trojan. Okay, so the thing is the last point that I was saying, that if somebody tampered the circuit at the time of fabrication, okay, so that is called inserting a hardware Trojan, and it happens whenever the design company who is designing the hardware is not fabricating it, rather it is giving any third party for the fabrication of their chip. Okay, so so that time what this third party can do, who is in charge of this fabrication lab, is that they can actually see the netlist and then try to understand what are the most significant part of the circuit. Okay, and there they can add some additional AND gate lot or some logic which will certainly leak the information. Okay, then it comes as IC anti-counterfeiting. Sometimes what happens is that, suppose I have a laptop which is quite old, maybe 7-8 years old. Now I sell it to some local vendor and I bought a new laptop. Now all the parts of the motherboard might not be bad. Okay, so this local vendor does what? They take up some ICs from the motherboard, okay, which are basically aged IC, because I am using them for last 6-7 years, right? Now suppose another party goes to that vendor and ask for some kind of a repairment of his or her laptop, and they found out that the part which is good at my end was bad at that party's end. So what they will do, instead of giving that party a new IC, they will just replace the aged IC of my device to the new party and say, see, your computer is running good. Okay, so adding counterfeit ICs is a huge issue in supply chain, and there is a group in hardware security who only works on how to identify counterfeited ICs from a device. Okay, now so we have talked about cryptographic algorithm implementation, then we have talked about how we can make it how we can actually do some side channel analysis and make countermeasure for them. Even if we do all this thing, we face some issue while we implement this cryptographic algorithm, be it a hardware, be it a software, for a particular application. Okay, so today we will be mostly focusing on Puff, which is a hardware fingerprinting tool, and then we will talk about how to securely implement Puff for authentication protocol. So that is the title of the talk eventually. Okay, so now before going to Puff and all, let's cover some base, that what do I mean by secure implementation of protocol, why it is so important. Let's see some test cases in IoT. Okay, so suppose Alice and Bob wants to communicate with each other. Okay, so they went securely. Okay, so then they went to a security solution provider and they said that, see, give me a AES implementation so that I can encrypt and decrypt the data which has been sent between us. Now the security solution provider give this AES code to Alice and Bob, and also give them a secret key. Okay. Now this secret key is shared between Alice and Bob. Now suppose this security solution provider may have many other IC of AES, right? So next, another party named Mallory came to the same security solution provider and says, please give me an AES implementation. So the security solution provider might be good at implementing a algorithm in hardware, but it might not have enough knowledge about the underlying security assumptions, and it shared the same secret key to Mallory, which he has sent earlier to Alice and Bob. Now it's a threat. Okay, Mallory can actually decrypt the message between Alice and Bob if he comes to know that it is the shared key between Alice and Bob. The other thing may happen is that Bob is just a normal user. Okay, he might not know how to securely store the secret key in his device. Okay, as a result, somebody can do some active or passive attack like side channel or any kind of malware injection and all, and get the secret key out of it. Now this is another issue, and now this attacker can sit between Alice and Bob, decrypt all the data that has been passed, and can send some malicious data too. Okay, so it's not, hardware security is not only limited to designing only cryptographic primitive in hardware. Okay, it depends on how we are going to implement it in a particular technology so that it does not have any side channel leakage or any hardware trojan and all. Okay, now how we are going to implement that particular product in a particular process. Okay, how much the manufacturer can provide for security. Okay, cost is always a big factor for the manufacturers. And then the last but not the least, the people who are going to use this process, how much they are aware of the security assumptions. Okay, so the area that covers whole of it is the protocol part. Okay, and today definitely we are going to talk about the edge devices of Internet of Things, right? So now you might think that this is very stupid. Why will I share the same key with Mallory? Now you see some example and you will understand how the real protocol are vulnerable against this kind of protocol level attack. Okay, so let us first understand this logjam attack that happens in that was published in CCS 2015. So what happened is that RSA used to be used for a long time, maybe more than 20 years in the system, in different system. Okay, so people used to use RSA 512. That means the key length was 512. Okay, now what has happened is that there came some prime factorization attack in the literature. Okay, which was able to successfully break this 512-bit key. Okay, so now the cryptographers say that, okay, so there is an implementation based fault in the RSA. Okay, mathematically it was good. Okay, but people can now factorize this PQ. So n equals to PQ in RSA, the famous n equals to PQ. So now people, from seeing n, people can actually do this PQ division. Okay, so what we have to do, we have to increase the key. So they suggested that please do not use RSA 512 anymore. Please use RSA 1024 bit. Okay, but people were not so smart. Okay, so when OpenSSL incorporated this RSA 512, what they did is that the message that are going to be used by the client and server to agree upon the key exchange, they keep it same for RSA 512 and RSA 1024. That was targeted to keep the backward compatibility feature, right? Now, as a result, what happened is that MITM attack can be done between the client and the server. Okay. Excuse me. So what the MITM attacker will do, it will convince the client that the server is a legacy system, so it can't do RSA 1024. And it will convince the server that the client is a legacy system and cannot do RSA 512. Okay, so that's what they have done, and that's why this logjam attack name came. So for both RSA 512 and RSA 1024, the data packets format were same, and we can actually do this kind of attack to downgrade the communication and then break it using prime factorization attack. Okay, but when the tragedy was that even after this attack was proposed, only 10% of Alexa's top million HTTP sites replaced their certificates. Okay. Even knowing that this kind of attack exists, 14% neglected to change their private key, which was 512 bit. They might know that the key might have been compromised, but they were reluctant to change it. More than 80 million invalid TLS certificates was there in the network, such as modem, router, VPN, firewall, IP cameras. So the issue is mismanagement of certificate when there is a attack in the crypto system, because people have bought certificate which has their public key for 512-bit RSA, and they do not want to renew those certificates to get a 1024-bit key. Okay. Now, the second issue or the second test case. So this is a Philips Hue lighting system. As you can see, there are three things. This mobile phone, there is this smart lights, and this, I mean, this part is not very much visible. This is basically a bridge. Okay, this is the communication point between the smart light and the mobile phone. So when you buy this Philips Hue smart light, what will happen is that your mobile's MAC ID will be considered as the ID to control these lights. Okay. Now, the problem is that when the app was launched, they used to use the hashed value of the MAC address to create the username. Okay. Now, if somebody knows your MAC address, hash functions are limited. They can actually create hashed value of the MAC address and just use it to get access to the smart light. Okay. Now you will I mean now this is the difference. They have this hash thing, you know, that means they have idea about cryptography, but they don't know that when we connect the mobile phone or any device into a router, Wi-Fi router, how easy it is to get the MAC address. Just one command in Linux will give you the MAC address of all the devices that are connected to your network. So this is the lack in security assumptions. That this is what I was talking about, that the manufacturer does not have all the ideas about security. Okay. Now more devastating things are going to come. If you have a Wi-Fi adapter and Wireshark, you can actually get all the communication data between the mobile phone and the bridge, because all the communications are happening in plain text. So now that means that you do not need to waste your time to get the MAC address by running that command in Linux. Okay, you can just directly, so here, these are the commands. Okay, so this is the IP address of your device, and then this is the ID. Okay, and then this is a GET request. They're asking what is the status of the third light. Okay, so this can be seen in Wireshark, and you will know how to make a command, what is the IP address of the mobile, and how to create a GET and POST request in HTTP and break the communication and get all the activities that is happening in the bridge. Okay, so the whitelist that is there in the bridge can be easily compromised. Now, more devastating part that has come up is that in IEEE SNP 17, it has been found that all these lights were communicating with this bridge with ZigBee. Okay, and they are using the same AES-CCM key for all these lights. So if you break the secret key of one light, you can actually hack all the lights that are in the market with this manufacturing ID. Not only a particular smart light set, all the sets. Okay, so this is for each device type. Okay, so that is where we do not need to break AES, we do not need to break RSA or do anything. Okay, these protocol level mismanagement can actually hack your whole system, right? So no provision for key refreshness, everything is static. Okay, now third point is that everybody is very much excited about Tesla car. They're making cars which will be like automated. You do not need to even drive the car. Okay, so few researchers in TU Leuven has found out that both Model S and Model X of Tesla has a very bad authentication protocol. So nowadays, basically, if you see, you really do not need to enter the key to the car door, right? You just click the key fob and your door opens. And then using the key fob, you can start the car. Okay. So obviously, when you can do that, that means there is some communication that is happening between the car and the key fob. And that is something like RF communication that happens. Now, this kind of entry system where you do not need to manually enter the key into the car is called passive keyless entry system, or PKES, right? Now it has been found that there is authentication protocol for this particular PKES system, but what they do is that while they communicate, the car sends a 40-bit challenge, and there is a very specific encryption algorithm which actually is not an encryption algorithm, just a step of bunch of XORs. Okay, so that is called DST40. That's why this 40 is coming. So the input is 40-bit and the output is 24-bit. Okay, in AES what happens, if your plain text is 128-bit, your ciphertext will be 128-bit. But here the response set is much lesser than the challenge set. As a result, what will happen, there will be 2 to the power 16 challenges. For every 2 to the power 16 challenges will have a unique response. Okay, so you have to do a brute force of 2 to the power 16, which is very less, right? To get a correct challenge response pair. As a result, even if you are not the correct key fob, you can open the car. You just need to relay either some old packets, or you can create a new packet with the correct response and send it back to the car, and the car will verify the response, which is perfectly fine, and unlock the door. So Tesla car can be hacked very easily. That's my point. Okay. So actually there is no mutual authentication. The car does not know that whether the key fob is correct, and the key fob is also does not know that the 40-bit challenge that the car is sending, whether it is really getting generated by the car or somebody is randomly sending this 40-bit challenge. Okay. So protocol level vulnerability. Now another test case is that in CCS 2017 and 18, attack came up. The name of the attack is key reinstallation attack. Okay, so they target Wi-Fi. So if you see in the setting part of your mobile, or even in computer also, there are many security level, like no security. Then it comes WEP, when you try to connect your Wi-Fi router with your laptop. Then it comes WPA, WPA2, WPA3, and so on. Okay. So generally nowadays we use WPA2, and it has been found that you can actually abuse the design or implementation flaws in the cryptographic protocol to reinstall already in use key in WPA2 and in other protocol of IEEE 802.11. Okay, so what is the case here? So WPA2 actually use again AES CCMP. Okay, so it's kind of an authenticated encryption. Okay, it's not only encryption. So what happens in AES CCMP? We have two inputs. Okay, one is, no, actually three input: the plain text, the key, and the initialization vector, and we get a ciphertext. Now the security assumption is that if we reuse a plain text, the IV or the initialization vector cannot be reused. That means we cannot repeat the initialization vector. It always has to be new. That can be very easily done by a TRNG. Okay, I was just trying to relate the discussion with people who knows about few stuff uh, about hardware security. So this is the thing. That is why we need a cryptographic algorithm as well as a true random number generator. Okay. Now the point was that what the attacker was doing is that they were sitting between the client and server as a fake access point. Okay, and making the client join the fake access point and then do a replay attack between the client and the access point. And the attack was designed in such a way that you will reuse the same initialization vector again and again. Okay, so the way the protocol was implemented, it was not supposed to be done, supposed to be this way, but it was happening. So that is why insecure implementation of cryptographic protocol can break your system without even touching any cryptographic algorithm. Okay, so that's the difference, protocol and algorithm. So insecurity lives and breathes in the cracks between the abstraction layers. Okay, it's a famous quote by Thomas Julian. So the target of my work is basically to breach the gap between the cryptographic primitive and its secure use in protocol. Hence, we focus on implementing lightweight authentication and key exchange protocol for IoT using PUFs. Okay. So do you want to take up, maybe I can give a brief about PUF, and then we can have a small question answer period, and then again go to the protocol part. Okay, so what is PUF? PUF is nothing but a hardware. Okay, it can be a logic function, it can be a memory element. Okay, but the real beauty of PUF is that when you give an in-bit challenge to the PUF, the response that we get is sensitive to process variation or very unique to that particular device. What do I mean by that? So suppose I have an AND gate. Okay, so you know it has a universal truth table that for 0001110 I will always get 0, and for 11 I will always get 1. Okay, now wherever you implement this particular truth table, you will always get this output if it is a AND gate. Okay, but this is not the case with PUF. Though we are going to use this logic gates only to design a PUF, the output at different device where we implement the physically unclonable function will be different. Now the question is, what do we mean by circuit sensitivity to process variation? Okay, let us give an example again with the AND gate. So now you know that if I give some input to the AND gate, I will always get this set of output. Okay, but can you comment on how much time a particular AND gate will take to propagate the input signal to the output signal? So the propagation delay of a particular logic gate to uh, to actually generate the output. Okay, so this propagation delay is basically varies from device to device. That means if I have two different AND gate at two different devices, the time it will take to get the output will be different at two different devices, and that comes due to some manufacturing process variation while we are fabricating the chip. Okay, So physically unclonable function actually exploit these property. So instead of thinking about the logical output, it think about how much time does it take to create the logical output. Okay, how it can do so, we will see. Okay, so now you can see that for PUF it happens that if we give a challenge to two different chip, the response will be different. Okay, so it has this following properties. It has this unclonable, unpredictable, instance specific system behavior. It is easy to design and fabricate but infeasible to replicate, because you cannot actually replicate the propagation delay of a particular device. Okay, it will be device specific and it will be determined only when you are manufacturing the particular device. It cannot be cloned from other device which already has been manufactured. Okay, it offloads computational expenses, and it has relatively low hardware over it. Okay, so it's really good candidate for an unconventional cryptographic primitive for resource constrained devices. Okay, now let's see what are the properties of PUF. Okay, first of all, because it is a hard logic function, it can be considered as a Boolean function, and given a PUF and a particular input x, it is always easy to evaluate the output. That is y equals to PUF x. It is very easy to evaluate y. Okay, now PUF x contains some information about the identity of the physical entity embedding the PUF. That means it will be unique to the particular device that is embedding the PUF hardware. Okay, now reproducibility. Okay, we can repetitively create y by inputting x to the PUF circuit. Okay, some error tolerance will be there. It will be unclonable. Given a circuit, given a PUF circuit, I will not be able to create another PUF circuit. Okay, unpredictability. Suppose I have given some input to the PUF, get the response. Now if I take another random challenge which I have not given as an input earlier, it will be very hard to predict what will be the output. So that's what unpredictability means. Okay, now comes one way. That means given a y and the PUF circuit, it is very hard to say what is the value of x for which we have got y. Okay, finally tamper evident. That means if somebody changed the circuit a bit, the PUF will not act as it used to act. Okay, so it will be changed something like PUF dashed. Okay, so now why do you use PUF? We want to get rid of this secret key issue, because secret key, if we implement them in a particular device, then we have to refresh it, we have to buy a certificate for it. So that's why we tried to do that. We thought that can we do keyless authentication, and that's why we thought the researchers has thought about using PUF based keyless authentication. Now let us understand that how we are going to evaluate this PUF. Okay, so what happens is that as you can see here, we have n stages in the hardware. Okay, and every stage has a particular logic. It will take a trigger, so the trigger input is same. Okay, but if the challenge to this particular stage is 0, then it will directly pass the signal. If the challenge to it is 1, then they will crisscross the path. How we are achieving this particular logic, we will see it. Okay, but suppose by using some logic function we are able to do it. Okay, so what will happen, as we have said, that this path, this path, this path and this path have different propagation values, though they are actually propagating the same input. See, if it is 1, then the 1 is going here and 1 is going here. Okay, though they are propagating the same input, that means we are not concerned about the result of the logic. We are just concerned about how fast or how slow the input trigger is passing over a particular stage, right? So now the thing is that we have a sufficiently large stages, like n can be 32-bit or n can be 32 or 64 or 128, and we give a 32-bit, 64-bit or 128-bit challenge. Okay, now given this challenge, we see that whether the input trigger comes at this D input first or in the clock input first. Okay, so why? Because suppose the D input comes first and the clock input comes after that, this one. Okay, so as a result, when the clock input will sample the D input, it will get a 1. Okay, so it will give a 1. If the clock input comes first and the D input comes later than that, then the clock input will give a 0. So now you can understand that how they are leveraging the propagation delay depending on the challenge. So now if there is n stages, there can be 2 to the power n possibility of giving challenges. So my given n stage arbiter path, I have 2 to the power n, that is exponential number of challenge to the path. But the response is here is either 0 or 1. So now if the response is 1 or 0, I cannot directly say that for which challenge I have got this 0 or 1. Because for many, half of the challenges I will get 0. And for half of the challenge, I will get 1, depending on what challenge I am giving. So that's why this invert thing does not happen. Okay. Does anybody has any question till this part? Anything? Don't hesitate.
Good evening, ma'am.
Good evening.
Ma'am, I just want to ask that how minimum stages should be there to get different response?
See, this is a very nice question. So suppose we give 3 stage. Propagation delay are very small. Okay, maybe if we just give the D flip-flop after 3 stage, it will always be a rest condition. Okay, so experimentally we have seen that 32-bit or 64-bit or 128-bit. So I specifically prefer 64-bit because in that case what happens, your critical path delay, if it is 128-bit, then the critical delay will be a lot. So I have seen for arbiter path 64-bit challenge is, or 64 stage arbiter path gives us good enough result. Okay. Similarly, as you are talking about TRNG, in TRNG also we use this chain of odd number of NOT gates or buffer, right? So there also, when we implement TRNG in FPGA, what we have seen that sometimes if the chain is too long or the chain is too small, the TRNG becomes very unstable. So that is why repetitively we have to change this parameter and check exactly how long I will keep the RO so that I get very good quality TRNG. Okay. Now, so I was talking that how we can actually make this stage. Okay, so we can make this stage using two 2x1 multiplexers. Okay, so this is the input which will be always 1. Once means that I am triggering the path. Now you can see that this input will go to this path, this 0 path. So this path and this path is symmetric, and this path and this path is symmetric. So the challenge has to be designed in such a way that if it is 0, these two paths will be selected, or if it is 1, then these two paths are selected. Okay. So there are many implementation level tricks is there to implement a path when we do it in FPGA or in ASIC. Okay, we have to write a lot of constraint that these, so that these paths are really symmetric, or at least we try to make it symmetric as much as we can. Otherwise, what will happen if there is one path which is like moving throughout all the lookup tables and coming to one, then one path will always be longer than the other. As a result, your response will be biased. So if the outputs are not uniform, that means for a arbiter path, as the output is like 1 bit. So if there are 2 to the power n number of challenge, ideally for 2 to the power n minus 1 challenges, the response should be 1, and 2 to the power n minus 1 challenges, the response should be 0. So there is some architectural technicalities that we have to maintain when we actually implement PUF in the FPGA, right? So, but today we are not going to talk about all these things. Okay. So for now, it is just enough to understand that we can create such kind of a hardware which will be unique, whose output will be uniform. The output will be unpredictable, and the output will be reliable. Okay. So these 4 factors should be there to use a PUF as a authentication authentication service. Okay. Now there are other kind of PUF also. So there is called ring oscillator PUF. So what happens is that in ring oscillator PUF we have this odd number of NOT gates. Okay, and the output of the NOT gate goes back as an input. Yes. Anybody has any question? Okay, I think that was just a by chance unmute thing. Okay, so now when we so suppose I have this kind of ring oscillator, maybe n number of such ring oscillator. Okay, so now when we trigger this ring oscillator, what will happen? They will flip between 0 1 0 1 0 1 0 1 0 1 0 1. Okay, now but because there is a difference between propagation delays, the frequency at which they actually move between 0 1 0 1 0 1, that will be different. Okay, so what we exploit over here is that we give, sorry, just a second, we give challenge to these 2 multiplexers. Okay, and half of the ring oscillator are connected to this mux and half of them are connected to these mux. Okay, now depending on the challenge, we select 2 ring oscillator and calculate their frequencies. Now if the frequency of the upper mux is greater than the lower one, then we say that this ring oscillator, I mean the output of the PUF is 0 or 1, and if the less, if it is less, then the vice versa. Okay, so we compare the frequency of 2 ring oscillator. The faster oscillation is randomly determined by manufacturing the process variation. And the disadvantage is that the exponential hardware requirement. So if I just change challenge bit from k to k plus 1, you can understand that I have to add 2 more such ring oscillator. So that's why ring oscillator cannot be very like I cannot make a 64-bit ring oscillator. Then I have to have 2 to the power 128 such ring oscillator, right? So that's why if I need a cryptographic key in my own device, okay, so in that case I can use ring oscillator where I need a small secret key. But if I need authentication, unlimited authentication, then we have to go to this kind of arbiter path, because adding one particular challenge bit will just add up 1 stage here, right? So definitely the hardware overhead less in arbiter path. Okay, so yeah, so this is a visualization that when we implement this ring oscillator frequencies in different FPGA, you can see the signature are different. So it can rightfully act as a physically unclonable function, so as the arbiter path. Okay, so now how do we do path-based authentication? Is that we send the challenge while manufacturing, we send the challenge and we get the response, and we store this challenge response pair in a CRP database. Okay, so this is much before deploying this PUF circuit into the real insecure network. Okay, so we assume that these challenge response pairs are securely stored in a particular database, right? So now after creating these challenge response pairs, we deploy them into the insecure network, and then what we do at the time of authentication, we select a particular challenge, send it to the PUF, get the response, and we match that whether these responses are same or not. If they are same, then we say that this authentication is actually successful. Okay, so this is what has been proposed as a naive authentication of path based thing. Now there are many problems here. Okay, first of all, after some time we will be out of challenge response pairs, right? Because so there is a problem of limited authentication. The reason is that we have to discard the challenge response pairs once it is used, because if we send this challenge response pair in plain text, the attacker can see this pair, right? Now suppose at later point of time, if the verifier wants to verify with the same challenge, the attacker can sit between the server and the puff, and can pretend to be a valid puff because it has the correct response. So replay attack. So to stop replay attack in the naive path based authentication, we have to discard the challenges, right? But that will again lead to limited authentication. That at some point, the database will be exhaustive. Okay. So what did we do to create a path-based secure communication protocol to get rid of these issues? Okay. Before that, do you want to? Do we have to take any break or something?
Yes, ma'am. Yeah, you can take 5-7 minutes break.
Yeah. So I would request that if anybody has any question, please let me know. Yes, I think there are questions, a lot of questions. Okay. Just a second. Can somebody read if where can I? Somebody raised hand, but now I cannot see it. If anybody has any question, please speak up. Okay.
Good evening, ma'am.
Yes. Please tell me.
Ma'am, in ring oscillator puff, it generate only one bit response. If you want to generate multi-bit, then what is the modification?
Okay. First of all, then don't do it with ring oscillator puff. Okay. First of all, if we want to create a multi-bit response ring oscillator puff, then the hardware will be huge. One thing that you can do is that either you can use arbiter puff, because then to create a 5-bit response or 6-bit response, you need to create this kind of delay chain 5 or 6 times, right? I will share one design that I have used for puff-based protocol to generate multi-bit response. So what I have done, can you see my screen yet? Let's go to that part because we have covered it. I think I can talk about it. Yes, this one. So what I have done is that I have taken these 5 arbiter puffs. Okay, I have given this challenge to this puff, and instead of sending the arbiter the top and bottom of a particular arbiter puff, I have taken this top of these 2, then again top of these 2, again top of these 2, and top of these 2. Okay, similarly bottom of these 2, bottom of these 2, bottom of these 2, bottom of these 2. So in this way, using this 5 arbiter, 5 delay chain, you can actually create 20 such output. Okay, so now if you need, if you want, you can stop here. But what I did is that because of some reason, we are not going to that thing today. So what I have done is that I have just XORed every 5 output and get the final response as 4-bit. Now you can say that, ma'am, this 4-bit also not enough, because suppose I want to create a secret key from path and want to use it for AES 128. So in that case, what you can do is that you can add a LFSR on top of it, linear feedback shift register. Okay, this is what I have done to generate 128 with secret key from Puff. Then what we do, we send one challenge
Hello.
first.
Yes, ma'am.
Hello.
Hello. Yeah.
Am I audible?
Yes, yes. Ma'am,
Yes.
60 volt for linear feedback shift register using for all 5 LFSR. This is basically, ma'am.
No. I'm just using one LFSR.
Yeah, one LFSR. How much bit, ma'am? 32 or 64 bit?
64 bit.
So according 64, ma'am, 2 की power 5. According 5 block for PUF, 5 arbiter PUF will be using. So per PUF, ma'am, how much encryption and decryption AES data symmetric key will be per PUF will be using arbiter PUF. Encryption time comparison as well as per symmetric key encryption AES methodology according.
Please frame your question again.
5 PUF for per PUF, mama, encryption and decryption key, AES key. I'm asking to that. So symmetric per PUF, how many number of key symmetric key will be using for according that platform of LFSR for particular LFSR 64 bit.
Okay, you are mixing a lot of things. Suppose you need can you see my screen? Can you see my screen? Yes. Suppose you want to run a AES algorithm. Okay. For that, you need a 128-bit key. This is what your final target, right? Yes or no? Is it your final target?
Yes, right. Ma'am.
Okay. So now the construction that 54 BAPUF I have just shown you has 4-bit output, right? Do you agree?
Yes, ma'am.
Yes. Now somehow we have to expand this to get this 128-bit key. What I am telling is that you take a LFSR which is 64-bit. Okay. Now the challenge, the main challenge, you feed here. Feed the 64-bit challenge to this LFSR. Okay, so this challenge will act as a seed, which we call it in general term for LFSR. Now, what you do, you run this LFSR for 32 times. Okay, so this will go through 32 stages. Sorry, this will go through 32 stages, and each of these stages can act as a new challenge to the 54 BAPUF. Okay. Now for each of these 32 challenges, you will get a 4-bit response. So now, after you have applied these 34 challenges and collected all these 4-bit response, you will have a total 32 into 4, which is 128-bit key. Now you use it for AES. Do you understand?
Yes, ma'am. Ma'am, this is for one seed, ma'am.
This is for one. So from one seed, you are generating 32 challenges, feeding them to the puff, getting the response, storing them in a register, and that will serve as a key. Now you can do it for your ring oscillator puff also. Okay, what you can do, you can if you want to create this you can use just one arrow puff, which may be suppose 8 stages or something. You feed the seed.
Hello, ma'am. Hello,
Yes.
ma'am. This is RO puff will use for if you use 3-stage ring oscillation and 5-stage ring oscillation, then it will be model you use, ma'am. Same. What are
You tell me. 3-stage means what? What do you mean by 3-stage, 5-stage?
3 stage, ma'am. 8 output, ma'am. Regarding that.
Yeah, 8 output or 8 arrow?
8 RO, 8 RO, 8 RO.
Yes, that means your output is 1 bit. Output is how many bit?
Ma'am, output, ma'am.
How many?
One output, ma'am.
Yes, yes. So this is what I am saying. Suppose you have whether you have a 3-stage arrow or a 5-stage arrow, your output is always 1, right? 1 bit. So what you can do, you can just add a LFSR in front of the arrow. You can give a 64-bit, or sorry, not 64-bit, 3-bit. Oh, wow. Okay. Okay. Okay, yeah, because 3-bit LFSR will not work. Okay, so then what you can do is that you can give a 64-bit challenge to the LFSR. Okay, now you can so basically what you can do is you can run it maybe for 2 times, that is 2 stages. Okay, so you will get 64-bit plus 64-bit. Okay, so total 128-bit. Now you can take 3-bit, 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 3-bit as much as you required, or to get a 128-bit, basically we will be needing 3. Sorry, one second. You need a 128-bit response if it is AES 128. So for 128-bit, basically 128 into 3. This much bit you need from the LFSR, right? So given this, you run LFSR. I think you have to run it for like 64-bit plus 64-bit 6 times. Basically, you have to do a 6-stage. So that's how you will get total 128 into 3 states, I mean bits. Okay, and then you store them in an internal register and plug in 3-bit karke and use the same arrow and get the response, which is again 128-bit. Clear?
Yes, ma'am.
Yes. Okay, so I think we can start now. So now we will see that here to describe the protocol, I have assumed that my path is also multi-bit. Okay, so now what we will do that there is a server and the node. The server will send some challenge and the node will get the response. There is no storage in the resource constrained nodes in the lowest level of the architecture. Okay, so now we will change the authentication part. So the enrollment part is as same as the puff1. Okay, but in the authentication, we will do something. Just don't get scared by seeing it. We will discuss slowly. Okay. So now, suppose node 1 wants to talk to node 2. Okay. So here the assumption is that the server has the CRP database of both node 1 and node 2. Now, when node 1 wants to talk to node 2, they will send a request, which is node 1, node 2. And now it will select 2 such challenges from both of their CRP database. Okay? Now what it will do, it will create some delta value, which is nothing but the hash of the responses and a particular timestamp. So why this timestamp is important? The timestamp picks up exactly when the server has started processing the authentication request of node 1 and node 2. Okay. So what has happened is, as a result, this delta 1 and delta 2 will act as the identity of node 1 and node 2 for that particular authentication run. Okay. Now, we cannot openly send this timestamp to the nodes. Okay, because otherwise they will be able to understand that when the process has started and can forge the authentication protocol, right? So what it will do is that it will take the timestamp and XOR it with the responses. Okay, so that means we are hiding both response and the timestamp with each other. Okay, so now we can send the challenges directly with the hidden timestamp as well as the response. Okay, to both node 1 and node 2. Now, because node 1 has this puff1 and node 2 has this puff2, they can actually characterize these challenges, get the response, and XOR with the hashed timestamp. So the TS1 is nothing but TS XOR R1 R2, and then it will again XOR it with the responses. So ideally it will get back the timestamp. Okay, now once it has got back the timestamp and it already knows these responses, they will make the same hash. So ideally this ID1 should be equal to del1 and this ID2 should be equal to del2, because both of them has been generated with the responses and the actual timestamp. Okay, now it will do some calculation. So this is generating this is for generating public private key pair for a particular node. So here we are not considering symmetric key cryptography. Okay, so how we can generate a public key and private key pair, and then we can also validate it. That is what we are going to see over here. So what we will do, we will create a P point which is hash of C1 XOR C2. Okay, now the public key will be T.P1 and the private key will be T.ID1, where T is a random value which has been taken from a finite field over a prime Q. Okay, so here we have assumed the elliptic curve cryptography. So they follow something called discrete log problem, elliptic curve discrete log problem, ECDLP, where if you know P1 and you know K1 pub, you cannot get back to T. So we have used this property to create this public key and private key pair. Okay, now the next hurdle that comes is that I have to, the node has to send this public key to the server so that the server can verify the public key on spot. So that is how we are getting rid of this certificate authority for validating the public key. Okay, so for that, what it is doing, it is creating a hash with the ID, which also needs to be mapped with del1. Okay, the P1, the public key, and there are two secret in the hash, which is the response and the timestamp. Okay, so why we are doing so, why we are adding these responses and the timestamp into the hash. Suppose I have a message in, okay, I do hash him, okay, and then send this message digest and the message in the wireless network. Okay, now somebody wants to tamper this message. So what the attacker will do, it will change m to m dash and discard the hash of m thing and add a hash of m dashed, right? So if somebody is validating that whether it has got the correct message or not, they will not understand that in between the message has been altered altogether. Okay, so we cannot let this happen over here. In that case, what will happen? People will tamper the public key and replace their public key with the node 1's public key or node 2's public key. Okay, so that is why in the hashed part we are adding something similar to the key. Okay, so someone who has the key can actually verify the hash. So you must have known about this keyed hash function, right? So this is nothing but a keyed hash function where key is generating from the puff. Clear? Anybody has any question? So far?
Hello, ma'am. Good evening.
Yes.
If we try to design TRNG for blockchain, then how much bit we required?
Do you have any specific question about the content that I am talking about, whatever I am telling right now? Do you have any specific question about that?
Yes, ma'am.
Do you have any query about the part that I am talking about now?
No, ma'am. It is related to the TRNG and blockchain.
See, it depends on what kind of blockchain framework you are making. Why you are using the TRNG? It's very hard for me, just abruptly say about it. Say about it.
We are trying to design TRNG as a nouns.
How you have to first understand that how many bit nonce, how many bit you required for the nonce. Yeah, so I think if anyone else has any question about the session that we are having, you can let me know. Okay. Okay. So now, this is where we were, that to send the private key, we have to make a hash of it and add some keyed hash function in between. Okay. So now when we send this ID P1 and K1 pub and the hash value to the server, then the server first check that whether this ID1 is equal to this del1 or not. Okay. Now, so if it is okay, and because the server knows the responses as well as the timestamp, so it can also make out this hash value of this ID1, P1 and Q1 pub. And if that is equal to the D1 that it has got, then the node 1 will be authenticated. Okay. Similarly, this node part and this node part are actually, node 1 and node 2 parts are absolutely symmetrical. So they will also create this ID2, P2, K2 private and K2 public, and then it will send this public key, the P2 and the ID2, to the server by adding a message digest using hash with the response of the challenge 3 and challenge 4 and the timestamp. Okay. So now the server, because it has this access to this CRPs, they can actually authenticate node 1 and node 2, as well as they can authenticate that whether this public key has been truly generated from node 1 and node 2, because no one can actually predict this R1, R2, R3, R4 except node 1 and node 2, right? So now once it is done, the last responsibility of the server that is left is that to forward the public key of the node 1 to node 2 and the public key of node 2 to node 1. Okay, so what we do for that, the same thing that node 1 has done before. So we take this information, which is this identity, the P2, the K2 public, and yes, sorry, hello, any question?
I think no, ma'am. You can continue.
Okay, so so what we will do is that we will make the hash and keep this response as a key to the hash, and then just forward this. See, you can see this ID2 P2 K2 pub, ID2 P2 K2 pub, along with just the new hashed value. Similarly, ID1 P1 K1 pub, ID1 P1 K1 pub, that has been forwarded to node 2. Now, node 1 has access to these responses again, this R1 and R2, because it has the respective challenge. So it can validate that this public key has been truly sent by the server. So that is how node 1 is also validating that the data that is coming is truly from the server and from no one else, because the server only has access to its correct response. Okay, so so what we see, or the takeaway from this particular part, is that there is no requirement for the certificate authority. Two party can anytime create these public private keys and generate and validate it using the server. So yes, one thing is that server always has to be present there to validate the public private key pair. Okay, but that is true even if we consider this Wi-Fi system or whatever. We always have this router or this base station, someone under whose jurisdiction a set of nodes are working, right? So they can take up this responsibility to generate and to help them in generating and validating the on the fly public private key pairs. So in that case, we do not have any requirement for secure channel for transferring the secret key, which is a major block in certificate authority based system. Now, as we have seen, both nodes and the server actually validate that whether the message has been truly generated by the other using this keyed hash function. We use the timestamp to stop reply attack, and we can use the public key private key pair for every protocol run. Okay, so now this part I am not going into too much details because there are a lot of math involved. So I will just give you a brief idea that. So now can you tell me that when a sender A wants to send some message to receiver B, which key it should use to encrypt the message? Can anybody tell me? Okay, so basically, if say A wants to send a message to B, it has to use the public key of B. Okay, and then it will be decrypted by the private key of B. Okay, so for encryption, we will be using public key because it is, yes.
Ma'am, at a sender end, public key will be encrypted, and at the receiver end, decrypt key will be receiving at the through decrypt block through private key in terms of.
Yes.
In communication protocol norms, basically secure communication in sender end encryption key will be using and in as a public key, and in receiver end private key in terms of decryption, decrypt key.
Yes, yes. If it is a asymmetric key cryptography.
Yes, ma'am.
Yeah. Okay. Now, suppose node A has sent the message, and later on it denies that, okay, I haven't sent the message. So that means it is saying that the message that you have got has not been sent by me. So how we will stop this? Okay. So this is called repudiation attack, that denying later on that I have sent a message. Okay. So for that, what we have to do is that, along with using the decryption key of the receiver, we also have to use the private key of node 1 or the sender, right? So that while we are decrypting it, the receiver will use its own private key, as in general encryption decryption happens, along with the public key of node 1. So we have to use two keys. At the time of encryption, we have to use the public key of the receiver and private key of the sender. And at the receiving end, we have to use the private key of the receiver and the public key of the sender. Why so? Because a message which has been at the time of encryption of which we have used the secret key of a node can only be successfully decrypted by the public key of the particular node, right? Otherwise, the message will be gibberish. So now the node or the receiver has a proof that as I have successfully received the message with your public key and my secret key, that means you have used my public key and your secret key to encrypt the message. So later on, you cannot deny that I haven't sent you the message. Okay, so that is how we stop non-repudiation attack. I mean, we enable non-repudiation. Okay, so now I will come to the experimental setup part. So we have used Puff. We have actually designed and implemented the Puff using Xilinx ISC design environment 14.2. So now the proposed prototype has been implemented using a combination of Intel Edison board and the Digilent Nexus 4 board comprising of RTX 7 FPGA. Now the number of slides required. So I have used, basically this time I have used LSPuff, lightweight secure puff, and later on I have used this 540 puff. But for LSPuff, it took around 547, 288, and 134 slice registers and lookup tables. The power consumption of the puff circuit reported by Xilinx XPower Analyzer was 0.044 watt. The software implementation of the elliptic curve cryptography, as I said, was done by Miracle Crypto SDK. So for the encryption decryption part, I have not used any hardware implementation. Only the PUF part was implemented in the FPGA, and rest of the part we have run into this Intel Edison board, and we have used this Miracle Crypto library. The executable took almost around 512 kilobyte of memory on the Edison board. So it includes the protocol part and the crypto library part. Okay. And later the latency overhead incurred running the end-to-end scheme was approximately 480.11 millisecond on average. So now you can see that this particular latency also incurred this serial input giving to the RTX 7 FPGA and serial output taken from the RTX 7 FPGA. Nowadays there are a lot of Xilinx board like Cora Z7, Cora Z-Turn. So what they are doing is that they have this ARM processor and an FPGA merged together in a single SoC, system on chip. Okay. As a result, you can write your protocol your crypto library in the ARM part, and whatever you need to implement in the FPGA part, you can do it into the. They also use RTX 7 FPGA actually. Okay, RTX 7 FPGA, and as a result, this latency will reduce drastically if we use this kind of FPGA boards, which has an inherent inbuilt uh, ARM processor. Okay, so now we have used pairing to do this integration of the sender's private key and the receiver's public key thing during the encryption decryption. So these are the execution time and the clock cycle count, and we have used four different hash functions. The hash function is basically the same. We have just added a few wrapper. That's why you can see that the timings are almost similar. So there are four types of hash function or the wrapper function we have used to map from one particular set to other. And so the clock cycle for tape pairing was around 1,950,000. For hash 1 it was more than 3 lakh. For hash 2 it was 22, which is a very small sharp 512 code. And for hash 3 it was 670, and hash 4 it was 350. So as a summary, I can say that we have developed and described in details a lightweight protocol for authentication, key exchange, and secure communication protocol applicable for hierarchical architecture in the IoT framework. We have also assumed that the CRP database is stored in a secure server, and even if the adversary has access to the database for a limited time, he or she will not be able to retrieve the private key of the legitimate user, and also would not be able to decrypt the data transmitted over the network. However, there is a possibility that the compromised server can make the legitimate device communicate with an illegitimate or malicious node. So from the implementation perspective, we have also presented a low overhead hardware software co-design of the proposed architecture on an IoT testbed. Okay, so this is one part. Now I would request that in case if you want to ask any question.
Good evening, ma'am.
Yes.
Ma'am, how we calculate the area on FPGA board?
Okay. So when you write the Verilog code in Xilinx ISE or Vivado, first you synthesize, right? The design. Have you ever
Yes,
run
ma'am.
any Verilog code in Xilinx?
Yes, ma'am.
Yeah. Okay. So now you synthesize and then you implement the design for a particular FPGA, right?
Yes, ma'am.
Okay. So now when your implementation is done, what have you used, ISE or Vivado?
Vivado.
Okay. So in the project, in the left side, you can write it, you can right click, and I think somewhere there is a provision to generate full report. So if you see that report, you will find that after placement, how many register, how many lookup table, how many slices has been used. So for every design, after the implementation, they give you an estimate of the used lookup table, flip-flops, and slices. Okay, so just
Yes, ma'am.
Google search that how to get the hardware overhead or how to generate the hardware overhead report for ISE Vivado. Okay.
Okay, ma'am. Thank you.
Any other question?
Hello, ma'am.
Yes.
Yeah, regarding ma'am, different type of test suite in an IST standard regarding that. So
Yes.
NIST SP800 for different TRNGs, calculation of different test items like a frequency, more about test block frequency. So, ma'am, how is the data collection according symmetric key and public key as well as asymmetric key, private key? Accordingly, information to be submitted TRNG implementation. So, regarding that, ma'am, how is the p-value and proportion in different test to be calculated for different key in symmetric key as well as say cryptography public key code and as well as private key cryptography private code for different tests will be I am asking to that, ma'am, regarding.
Okay, first you shorten your question. I mean, it's a very long question and I cannot understand anything from it. Let me rephrase your question. So you want to say that you will have a TRNG, and using that TRNG, you are going to generate key for symmetric as well as asymmetric key crypto system, right? Is that so?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay. Now, the thing is that the quality, I mean, there is no relation between how many key bits you are generating with the quality of the TRNG or the NIST test. So it's not like that you will generate multiple like if you are talking about AES 128, you do not need to create 128-bit multiple keys and then feed them to the NIST test suite. There are test suite which will take GBs of TRNG raw bit and give you the result. Now later on, whether you are going to use those data for, I mean, those TRNG bits for a AES key or a private public key, that is up to you. So the NIST test does not depend on where you are going to put that TRNG data.
Dependency depend upon time or size of TRNG.
What dependency?
Decryption time versus size of TRNG text files. I am asking to that.
How? Your decryption, if it is a AES 128, it will always,
execution times, ma'am, different size of TRNG, different execution times in seconds.
You are not using TRNG in your decryption, right?
Okay.
You have to understand TRNG is a different block and encryption decryption is a different block. You are just using the data that are getting generated from TRNG to create the key. It has no role in the encryption algorithm or decryption algorithm.
Okay, ma'am. Okay.
Right? So AES has a specific set of operations that has nothing to do with TRNG. You are using TRNG to generate random bits. That's it. Now, whether this random bits will be used as a nonce or whether it is going to be used as a key, that depends on your application. Okay, but to do this NIST testing, you have to generate a lot of TRNG data. Maybe you have to run your TRNG for a long time. So time dependency come how much data that you are generating from the TRNG to do the NIST test. The more data you will give to the NIST test, the more good result, I mean, the more bad good it up to the design, more accurate result you will get from the NIST test suite. Now, after it has passed the NIST test suite, you know that the TRNG raw data bits that you have generated are truly random. Now you use it for nonce. Now you take 128 exact bits from it and use it for your AES encryption decryption. Okay.
Yes.
Don't mix them.
Yes,
All
yes.
these are different
in
hardware.
In summary, let basically limitations you said that clearly, low overthread hardware and software means what is means of implementation of low overthread in summary points.
Low what?
Low overhead.
Low overhead. What
Yeah,
overhead?
it was you summarized
Hardware.
implementation perspective, low overhead hardware and software co-design of proposed architecture in IoT test bed use summary points PPT.
Oh, okay. Yeah. Oh, acha, understood. Okay. So now the thing is that for my point of view, low overhead hardware software co-design means that I could have used a 128-bit arbiter path, right? That means which has a 128 stages, but that would have increased my hardware space. That could have increased the time to execute the path, right? So low overhead means I can work with a 64-bit 64-bit path instead of a 128-bit path and still get a nice public private key generation process. Okay, so and other things are so there are few stuffs which are there in my paper, is that it is not like I am proposing for the first time the path-based authentication protocol. Okay, there were a lot of other protocols which has been proposed earlier. Now, what do I mean by low overhead? It has many terms. One is that the hardware overhead of the path, hardware area of the path should be less. Second, the amount of memory is required to store the challenge response pair. So in my case, it was 64-bit challenge and 128-bit response. Okay, but in many cases, in many protocols, it was like more than 1,000 bits per challenge response pair you have to store. So that will increase the memory overhead of the server. So there is an extensive analysis of the proposed protocol with respect to the existing protocol. Okay, so that's why I have talked about low overhead in terms of hardware overhead, memory storage overhead, even latency. There are many protocols which take more time than 480.11 millisecond, whereas I have this serial communication. Their communication takes more than that. So low overhead comes from area, power, delay, and timing. So when you propose a design, you have to show a comparison that your design is better in consuming less power, consuming less area, consuming less time than the state-of-the-art literature. Okay, and I have termed it as a IoT test bed because this inter-edition board can be used to add many sensors and actuators. Okay, so it can be considered as a IoT device with which lot of these sensors and IoT components can be connected. So that's why I have used the term IoT testbed. Any other question?
Good evening, madam.
Good evening.
I have a question. Suppose we are having a algorithm symmetric cipher, and we have written it on Verilog and implementing on FPGA. Like you said, we can evaluate the area delay power. Apart from that, if we want to do a security analysis based on the algorithm and some existing algorithms, so can we conduct an evaluation through the simulation apart from using any this NIST test feature? Can we derive any inference from the simulations that our test bench simulations for security?
First question. For what purpose you use this NIST test suite? To validate encryption algorithm or to validate the quality of the TRNG?
Encryption, symmetric encryption algorithm. No, my purpose is I was asking that I am having a symmetric encryption algorithm. I have implemented it on FPGA. Then I want that I have added some additional architectures to it. So for security analysis, can we...
To do what? Additional architecture you have added to do what? For what reason?
Yeah, architecture for low power and delay. So that kind of trade-offs. But I also want to show the security aspect.
So, okay, let me think about it. So I don't think that NIST test suite is required for AES security analysis. So you have not changed the basic algorithm, right?
Yes, madam.
So you have just added or modified the hardware part so
Yeah,
that
yeah.
it takes less power.
Yes,
right?
yes.
So now you just need to so if you do not add that architectural part, the plain text ciphertext pair would be same if you add that architecture, because there is no mathematical change in the algorithm.
Yes, madam.
Have you checked that before adding the additional part, the plain text ciphertext pair that you used to get is same as the plain text and ciphertext pair,
Yes,
which
it is same. It is
okay.
same.
Now the only thing that can come up is whether from the power consumption perspective it is leaking any information or not.
Yes,
right?
yes.
So that means you have to do a power side channel analysis, not something missed around.
Yeah,
So
that I was asking. So is it possible through FPGA platform, or we need to go for some, because we sometimes we don't have that particular FPGA board which uses like we don't have. So we want to go with normal simulation. We want to do the analysis through simulation. Like we have for side channel analysis, we have certain boards.
Sakura.
So yeah.
Okay. So
But
if you have Sakura,
no, we don't have that. I was asking that through simulation point of view, can we do any inference? Like you are telling power analysis.
Yes, actually there is a paper which can help you out. Just a second. Yes, I got it. Yeah, so this paper you can see it talks about how can we create a leakage model, specifically power leakage model, before even deploying the crypto design in silicon. Okay, so I'm just giving you the link of it. So it's pre-silicon power side channel analysis, and because it is pre-silicon power side channel analysis, you really do not need the FPGA boards.
Okay,
right?
Okay, madam.
Okay.
And
I'm just
we'll go
sending.
through this.
Yeah. Yeah. So this you
you.
can do
Yes.
for simulating. This is what I am just telling you. So why does power side channel attack happens? This is because in AES we have 10 rounds, right?
Yes.
Right, and we try to use the same hardware for all the 10 rounds, right? We do not have like hardware for 10 different rounds. And what is the reason for that? Because in every round we have the same round function, that add round key, shift row, substitute, S box, shift row, mixed column. Okay, so it's from the performance point of view, it is better to use a single hardware for all the 10 rounds, and at the 10th round I will just remove this mixed column stuff. Okay, so that is the main algorithm of AES. Now what happens, the output of the previous round is basically the input of the next round. So these intermediate outputs are basically saved in registers, right? Now when we execute a round, this this output actually changes, right, and get stored in the same register. Okay, now you know that the power consumption which is required to transit from 0 to 1 in a particular memory element and from 1 to 0 are different.
Yes.
That actually leaks the power information from your crypto design. That is the main source of power side channel attack. Okay, so this particular paper does nothing. It just check, given a crypto design, what are the registers and whether their toggles are balanced. I mean, registers toggles are balanced or not. If they are imbalanced and it depends on the secret key, then it will leak information.
Yes, yes.
Okay, so for your modified architecture, you have to find out that whether this modified architecture has any impact on the registers, the amount of registers that you are using for your design or not.
Yes.
If yes, then you must do a analysis for your design. But if the optimized part that you have done so far has nothing to do with the number of registers that you have, then the main design and your optimized design will be as same level of vulnerable to side channel attacks.
Okay, okay, ma'am.
So you see this paper, I
Yes.
think you will get an idea about how we can do power side channel analysis in a pre-silicon stage. Okay,
Okay,
and
thank
this
you.
is actually a very much hot topic. You know, people. I mean, pre-silicon side channel analysis. If you just write it in Google Scholar, you will get a lot of paper on this.
Yes, yes, madam. Thank you very much.
Yeah, so you just take your design, do this thing. You just need to handle your registers. So this is what I was also telling to the other guy who was talking that that whether the TRNG will be vulnerable to the side channel attack or not. So if the last D flip flop, if somebody can understand that when it is 0 and when it is 1, seeing the power trace, then I think they can actually see the values of the TRNG. Any other question?
Ma'am, there is a,
Yes, tell me.
yeah, there is a question by Mr. Jagannath Prasad Mahanti. Maybe his mic is not working. Is there
Okay.
any possibility of modeling a man in the middle attack in this node server communication scenario?
Yes. So there is something called Cyther, ProVerif. These two are protocol verification tool. Okay. So if you have a protocol, you can write a pseudo code of your protocol in this tool. Okay. And then if you run the tool, they will tell you that whether your protocol is vulnerable to man in the middle attack, replay attack, unbounded access attack, and all. Okay, now they will what they do is that when you write the protocol in a certain manner in this tool, they create a graph, and then this graph has some secure path, so that will lead to the finishing of the protocol. And if there are some red path which is not reaching to the end node, that means there is an attack. Okay, and this graph path will give you an idea that whether your protocol has a MITM attack or a replay attack or nonce is right or not, whatever. So you can actually, I'm just writing these two names. One is Cyther and another is ProVerif. You can look into this. Yeah. Any other question?
Ma'am,
Yes.
how much arbiter puff will be reliable for 64-bit challenge? Reliability and
Arbiter puff
uniqueness.
is very reliable. With respect to temperature variation, arbiter puff is very reliable. But the problem with simple arbiter puff is that their uniqueness is very low. So that's why we do this zoring and all this thing to make it unique. That's it. Okay. From the reliability perspective, Arbiter Puff is very, very good.
Thank you.
Any other question? Okay. So, yes, anybody has any question?
So, Mahapatra sir, your voice is your voice is not coming. Sir, Mahapatra sir. 1 minute, madam.
Yeah, sure, no problem.
Okay, madam. I think there is no more question. Sir, Mike is having certain issue.
Okay. Okay, then I think we can finish this session then.
Yes, madam.
I have tried to cover a lot of ground on Puff and how we can create a protocol using the Puff. So further, if anyone has any other question, they can definitely email me and I would try to resolve the answers.
Okay, thank you, madam. Actually, this session was very informative and interactive also. At the same time, you have started from basic to again communication protocol, and you have ended with certain research example also, like pre-silicon validation and all. I thank you, madam, for giving us time in the evening and helping us, our student and researcher, to get new ideas to carry out their research in future. Thank you, madam. Actually, before ending, I request all the participants to just open their. I am allowing camera, so we can take a screenshot for all. And after that, madam may leave, and we have a MCQ session today. So kindly don't leave. All the participants be there for another 20 minutes. Sorry. Rajesh, you please take some screenshot. I am also taking. I request you to please take.
Yes, okay, sir. Yes, sir. I understand.
Okay. Okay. Thank you, madam.
Thank you. Thank you so much. Yeah.
Thank you. Sir is there, but sir's mic is having maybe problem. Okay. So I advise all of you, please be there. We made a quiz session on MCQ, multiple choice type question. So as part of that schedule, so I am just sharing my sharing the link in our chat box. 1 second. And already attendance has been opened, so you can also fill that. Okay, accepting response also done. for the quiz. Now it is 9:12. 30 questions are there. I advise you kindly complete it by next 25 minutes. By 9:35 p.m. please try to complete it. Just click on the link. MCQ will be appearing for you, and you can select whichever you find it is correct. Can anyone just answer me, like, are you able to fill responses?
Yes, sir. We are able
Okay.
to open it.
Okay, thank you. Mr. Pratik, you can get ma'am's email in her IIT Kanpur site. I advise please fill all the responses, all are required. And once you fill the response, it will not take another response from you. So please answer all questions, then submit the button by 9:34.